Нужно как сидеть, потом ты представишь, я выжил или как.
Много внимания мелочи.
Да, да.
Лежать, наверное, когда вам сидеть или стоять. Да.
Concave — это что по-русски?
Вогнут.
Вогнутый.
Да.
Окей, хорошо.
Но они же вогнутые, эти
Ну, понятно, я понял, да.
concave.
Это какое-то заумное слово или есть более простое?
Да нет, ну, звучит просто curved, конечно, не сказать, но concave, линзы вот оптические, они бывают concave, бывают вот...
А выпуклая как будет? По-английски.
Что-то я не знаю. А, да, конвекс и конкейв. Это вот типы линзочек, которые продаются для очков. Что такого?
Ну да, по-другому здесь так и не скажешь конкретно.
When should we start?
Sergey will come and we will start as usual.
I looked for you yesterday.
Yes,
I only found the
today and yesterday are my days off actually. I just came here for 7.
Nice.
Okay.
You just came to defend analytical job.
Good afternoon, PCS members and friends. Today we have a scientific seminars by Pavel Kozhevin. Our scientific host today is Dr. Sergey Konyakin, who will introduce our speaker. Sergey, please.
Okay. So, Pavel Kozhevin has obtained his master's degree in St. Petersburg University in physics department, and now he continued his research as a PhD student in Kavokin laboratory in St. Petersburg University, and also he's a part of Abrikosov Center in Moscow. And today he will speak about our collaborative work with KAIST on optically induced concave mirror polaritonic cavities. Let us welcome the speaker.
Okay, it's me. I think it's okay, Oleg. So let's start. First, as usual, outline. I will start with a few words about exciton polariton condensation physics, just as a reminder, who is not familiar with this system, with that systems. Then we will discuss availability of constructing cavity-like optical landscape in which condensate lives. And after that, I will show you some experimental results, which we model. So the next section is how do we model these results. And after that, I will throw small kind of semi-analytical approach talk. I will give a small semi-analytical approach talk. So let's start. First of all, we should see in which structure usually exciton polariton condensates are studied. This structure called microcavities. Microcavity is a multi-layered, usually gallium arsenide-based structure, which consists of 2 distributed Bragg reflectors. Between which standing wave of electromagnetic field occur. In antinodes of this standing wave, we can insert a set of quantum wells. So if exciton losses are small, if cofactor of that microcavity resonator is big, we can achieve so-called strong coupling regime of excitons from quantum well and photonic mode from microcavity. We can quantize their interaction, and the resulting quasi-particle is exciton polarity. This is the scheme of the structure is at the left upper side of the slide. The B chart of this picture demonstrates pumping scheme of or excitation scheme of exciton polariton condensate. We assumed and experimentalists used the red one. It's called non-resonant pumping scheme. When high energy charge carriers are injected in our systems by optical excitation in continuous pump scheme, then they relax due interaction with phonons and form so-called excitonic reservoir. Excitonic reservoir is a highly populated array of excitons which cannot scatter down unless their number is their particle number is sufficient in that state. So when excitons when the number of excitons become huge, they start to interact with each other, and this scattering leads to formation of exciton polariton condensate in zero of momentum area. So we have two general subsystems. First subsystem is exciton polariton condensate, which is fed by particles from exciton reservoir, and so the second one is exciton reservoir. The interaction between them is repulsive. So polaritons from polaritons interact with excitons by repulsion.
Oh, sorry, you have told some really interesting thing. So you told that from the exciton reservoir we do not scatter to the condensate until we have sufficient density in the reservoir. But normally, when simulating Gross-Pitaevskii equation, we put that scattering rate is proportional to the density of reservoir in the first power. So R times N reservoir. So in some sense, what you speak means that we should rather use maybe R square dependence. So it's some general notion to think of. Honestly, I don't expect that anybody can answer this, but this is some relates.
As I know, it was showed microscopically, which I cannot do because I don't be able to calculate Keldysh diagrams, but it has been shown that the interaction between this feeding strategy of polaritons in condensate looks exactly like this. So, but we further will talk about how we simulate that system. We also we just here need to know that the condensation of first particle here is is not governed by models that we will talk about later. At C plate of this picture, you can see usually dispersion at free pumping power, collected at free pumping power, below pumping threshold, at pumping threshold approximately, and above this. To give a sense of that system, I can show you some typical numbers for polariton condensates. The temperature of polariton condensates is usually pattern condensation is usually about a few kelvins. In our particular experiment, it was about 6 Kelvin. Usual effective mass of polariton in condensate is 5 magnitudes of photon smaller than mass of free electron, and usual living time of that quasi-particles is about 10 picoseconds. The typical heating length of this condensate in our simulations was about 10 microns. As I said before, we can control the potential and due to the excited condensates excitation scheme, we can optically control the landscape in which our condensate lives and from which our condensate feeds. As example, I can show you several peaks. The first peak is one which expired our work. We can consider a non-resonant pump which is shaped like that concave mirror like. In that systems, it was shown that pump-induced potential focus polaritons in some focal region. Here you can see another examples. First of them is extracted from experiment polariton condensate density and phase in ring-shaped pumping scheme, and the last one is pumping scheme which we called concave cavity. It's just two lenses put it in front of each other. This is also polariton densities distribution in real space. So let me show you some experimental results. Experimentalists conducted 3 sets of experiments. First of them, when these 2 mirrors are placed, concave mirrors are placed in front of each other, and we will call that case cavity. The second one is when one of mirrors is rotated by 180 degrees, and we will call this system a half cavity. And the last one is anti-cavity, when both mirrors are looking outward of the system. Here you can see high power real space, reciprocal space distributions of particles which were collected from experiment, and polariton condensate dispersion, which was also collected by experimentalists.
So what is the point of this? So you have these half and anti-cavity setups, which kind of like are no cavities, and yet you still have nice condensation. Is that what you? So what do I learn from this?
It's just example of which types of structure were studied. But in the next slide, I will point out what was.
Or let me rephrase my question. So you teach us before that you need a cavity to start the game with, and now you make an anti-cavity, which is a not cavity. So kind of like I think an anti-cavity means that that you do not trap efficiently photons in the cavity. Or am I getting something?
There is some misunderstanding because there is structured structure. There is a cavity in structure, which is formed by distributed back reflectors and so on. But this cavity is cavity formed by
the
lasers,
pump,
by pump.
I see.
Yeah, and they form the potential and feed polariton.
And why do I expect any difference in these fine differences between cavity and anti-cavity?
The difference is because in cavity case, if we consider only one mirror, we will see an effect of polariton focusing. So there, as I will show later, and it was also shown before, that polariton propagation length is bigger in cavity case, or if we compare it just to square box pumping potential scheme. So it was expected that if we put two mirrors and they form a cavity, then the effective interaction between the two polariton condensates will increase. So pumping threshold will decrease for that strategy, and their interaction will be stabilized. That was a proposal to this experiment and to simulations, which was made by Sergei.
And so what is the outcome? Then it doesn't matter, right?
Not simulations, but the proposal, only
No,
proposal.
but if I look at the experimental results, it looks like it doesn't matter whether I have cavity.
Yeah, because it is a high pumping regime. The difference is
closer to the threshold.
yeah, the difference was observed closer to the threshold, because as you can see here, here is reciprocal space condensate photoluminescence captured for cavity, anti-cavity, and half cavity, and some certain pumping power. And we see that condensation in gas space occurred first in cavity, and for bigger powers in anti-cavity or half cavity. So this fact was this fact.
How do you quantify the threshold at which condensation?
Yeah, it's about 13 milliwatts.
And how do these numbers differ for the other setups?
In that setups, this is about 36 milliwatts. So 3 times bigger than for pumping pressure. These pictures are placed here just for illustration. I think.
Far above, it's very far above the threshold. So
Yeah,
yes.
But the point is that the threshold changes by a factor of 3.
Yeah,
I don't think so.
No. Well, so then let me repeat my question again. So I take this setup, which is called cavity.
Yeah.
And there is some threshold power.
Yeah, there
which
is.
is 13.
Yeah.
So what is the threshold power for anti-cavity? If you can tell me.
Maybe 15.
Maybe 15, so it's not that different.
Not that different, but still it exists. It measures 5%, 10%, something like this.
So it starts with 13 milliwatts per cavity.
Yeah, for cavity, and for anti-cavity and half cavity is about 15 or 16 milliwatts. This effect is observable, but it's quite small. Yeah.
Okay.
But this effect was captured by experimentalists, and we had to explain it and to simulate it, and so on and so on. So
what's the difference? Because 3 pictures in the top right corner, they are very similar, I would say.
Yeah, they are very similar because the resolution of imaging system is do not allow us to see to resolve dispersion correctly. So
But this is the dispersion after condensation,
Yeah,
because it looks like a parabola before condensation, no?
this is dispersion before condensation for anti-cavity and half cavity, and for cavity case there is a small condensation pattern, condensated pattern here, but we don't see it in.
Okay.
It's an imaging artifact of optical system.
And question here, why do you even call it cavity? So what's the cavity? What is the meaning of cavity? Can you go one slide back, please? Yeah, so the real space condensate distribution it looks like between these two hotspots, so to say,
Yeah,
right?
yeah.
And you have some standing wave between them.
Yeah.
So you have some kind of like tunneling between them, you could say, or some.
Yeah.
So in that sense, it's like a cavity, right? So is that why you call it cavity, or is there any deeper reason why you would call this a cavity? And what happens if you just take one of them? One spot?
One spot. I will show.
One spot is just one spot, right? You just get one spot. With two spots, you get something interesting in between them.
In between them. Yeah. We
kind of
started interaction between two Z mirrors.
I see. And that's why you call it cavity.
Cavity. Yeah.
Can we see it
I
like
think
this?
for one spot, there was also some focal spot condensate.
Yeah,
There
we
was in between.
can
Yeah, it's like
we
here,
can hear.
in
We can.
the focal region.
I see.
That's maybe the most.
That's the reason why one would call this maybe a cavity. Okay.
So when I the transfers when I come back when I come here they were already being called cavity, and this is not my name. I just used one which was introduced by Sergey or maybe something else.
Yeah, and the guy's colleagues called the left guy cavity. Okay, so I propose to measure to measure the right pattern, which was called anti-cavity. Well, and importantly, the meaning was to keep the shape of the spots the same, but to tune the direction of interaction. So you see the symmetry is broken for each mirror, and how they oriented is important. But we wanted to keep the same geometric profile of each spot, and that's why we put the concave areas outwards.
Excuse me, can you explain this yellow spot? It's just some condensation of this. What is the yellow spot?
This yellow spot, this bright spot, you mean? You mean this one bright spot, yeah?
Yes.
So what is the color code? I think that's the question.
Okay. Their actual color is red, but let's call them yellow. Let's read them yellow. We have two polariton condensates. So they allocated at this bright spot, and these condensates have tails which overlap each other, and this overlap leads to interaction between them, like in Josephson problem.
And then to focus and to produce this spot, bright spot, you need some pumping profile.
Yeah, you need some pumping profile. You can use just two Gaussian spots.
Yeah.
But we studied that configuration.
So
and compare it to anti-cavity.
It means the role, qualitative role of pumping profile is just keep condensation for specific area.
Yeah.
So is it that is why for anti-cavity the tails are more spread out?
They were spread out. They were spread out to control the total amount of power, total amount of injected particles in your system. If you compare cavity and, for example, two boxes, it's hard to maintain the same total pumping power that you pumping power per area that you inject in the system. So if the total pumping power is different for cavity and something like that, it's just impossible to show what we are wanting to show. We need to maintain total pumping power constant in both an experiment and simulations, and so that's why we compare cavity and anti-cavity, or but not cavity and some kind of else.
Another question, and we have pictures on the left and also on the right.
Yeah.
What and pictures quite different in angle and rotates. And then question is what?
Pictures on the left are just pumping profiles, just reflected image of pumping scheme that experimentalists use. The pictures of the right and bottom are collected emission from condensate. Because when polariton die, it emits photon, and this photon carries information from condensate. So the technique of extrapolaton physics measurement is optical collection of photoluminescence in real space, in reciprocal space, in dispersion, or something like that. So the pumping and measurement system is fully optical.
I'm sorry, I have another question.
Yeah.
So in this case, space polariton condensate, for instance, on the most left picture, we apparently see some up-down asymmetry. What's the reason? It's just
The reason
bad
is
measurement.
it's just measurement difficulties. Yeah.
What do you say? Where is
Up-down asymmetry. You can see
asymmetry?
asymmetry. Yeah,
In which case?
for instance, the most left one, the middle one,
Intensity.
and they are expected to be symmetric with this.
In case, please.
Yeah, and they're quite asymmetric, I would say.
The first problem is an absence of defects in structure and imperfection of optical scheme. And the second more physically thing is that at high pumping power, you can absorb some limit cycles of condensate states or something more complex. And these pictures are integrated over time. Over a huge time, because typical lifetime of polaritons is about 10 or picoseconds. These pictures were collected in range of microseconds or even bigger, or milliseconds. So averaging picture can look very different if we compare it to something single shot measurement.
But look, even the pumping profiles are symmetric.
Yeah, the pumping profiles also are symmetric. It's also optical imperfection. It's also optical imperfection, but it is connected to spatial light modulators properties that experimentalists use. But they did what they can do, what they can do.
And I have a general question to everyone. How do you actually show such pictures, including arrow bars? What means, how do you make arrow bars in color plots? Very hard, right? So,
Yeah.
I mean, so you have to blur maybe the what? Colors.
Possible.
Possible.
Yes.
Intensity arbitrary units.
From 0 to 1. But there are still tons of imperfections. But so that's why we need to model the system to capture some physics from raw data. So how do we model our system? The approach was standard for extrapolaton physics. The main equation that governs evolution of extrapolaton condensate is Gross-Pitaevskii equation. It's a nonlinear type Schrödinger equation with non-Hermitian, which is non-Hermitian. Here we have kinetic term and some non-Hermitian terms which correspond to outcome of particles and income of particles to condensate due to polariton loss and due to exciton scattering to condensate. So the next two equations describe excitonic reservoirs. Active is reservoir which feed condensate, and inactive is a high energy reservoir which pumped by the laser. So and also at the right corner you can see some examples of steady states obtained for these equations by me in for example, ring shape trap, just Gaussian spot, and our cavity-like structure.
That's real space, everything?
Yeah, all is real space.
What dictates here the distance between the spots in the polariton density in the left bottom plot?
In the left bottom, the densities between the peaks, what defines
the distance between peaks?
Strength of interaction, strength of exampleton interaction, size of optical pump, and so on and so on. I hope we will publish publish a paper about that structures.
But isn't it just the angular momentum?
Yeah. The number,
so it's just a high M state.
Yeah. The number of the slopes is controlled by angular momentum which polariton condensate carry. It's about if, for example, you have angular momentum 10, you will see 20 slopes, and if you have angular momentum 5, you will see 10 lobes. But it's not a point of our talk today.
Actually, the question about why you really wanted to include diffusion into inactive reservoir, and for active you don't need it. In general, what is the profit of diffusion for simulation?
In general, the key reason of why we include dispersion term here is that interaction of condensate and excitons here is contact. If you want to see condensate from simulation, this condensate will overlap with your potential. But from some other experiments, which I don't want to discuss today, it's evident that the overlap of pumping profile and polariton emission could be very, very, very small, almost zero in experiment. So we have to assume some broadening of exciton reservoir. But for this work, we just can treat this diffusion term as some artificial broadening to take into account optical broadening of pumping profile or something like that. It's not key. It's not a key parameter for talk today.
And what is the part in these equations which is responsible for this angular momentum you mentioned? Where is that?
As in usual conservative systems, we can write angular momentum operator and to try to find eigenvalues for linearized problem.
It's an initial state, or
initial state of the. I will show you what we do in calculations. Initial state of the system. Okay, it's just white noise.
Yeah, but then what defines the angular momentum in these equations? Where is it popping up?
It's not presented here explicitly, but the angular momentum depends on total particle blue shift in energy that they have with fixed geometry. You can tune, for example, exciton-polariton interaction, polariton-polariton interaction. You can make it bigger, and after that, if you observe steady state, which is not guaranteed, the number of lobes will increase.
Yeah, but when you tell me I take these equations, I get that one. So then I can somehow change something miraculously, I will get a different number of lobes. So what do I have to change in these equations or what fixes the number of lobes in these equations? Or the blue shift, or whatever you call this. Where is this term which is responsible?
Repulsion interaction parameter, GR, polariton interaction parameter, GC.
So the numbers together will tell me at the end of the day how many.
Only after simulation. It's not quite easy to determine the total angular momentum.
Can I fix these parameters and get different numbers of lobes or not?
You just need to increase population of exciton particles and reservoirs.
It's a matter of different initial conditions then, in a sense, or not?
In principle, you should calculate the growth rate of these various angular momentum modes, as it was done by Nalitov and co-authors, I think about 6 years ago. And then you can draw a numerical picture where this growth rate, all these growth rates for various angular momentum. And usually the highest, the mode with highest growth rate will be your,
There is a mode
your
competition
state,
during-
which you will have there, yeah. But it's not, it depends on all these parameters of this simulation. So
it's not quite easy to tell you.
it's not apparent yet.
We
but
have that one's
you can draw
parameters.
some picture.
Which angular momentum the polariton condensate will carry. It's not that easy talk. There is a span of energy
Аналитический.
which can, there is a span of energy where set of this mode exists, and the mode with biggest growth rate will win this race.
Okay, so I got
It-
that.
it's-
Now my
it is
question
not-
is, how do I change the mode number of the mode which has the biggest growth rate? What do I have to do?
I think there was a picture in that paper that you basically, if you fix all other parameters, you just increase your pumping strength,
Yeah. You just increase it.
and then you will
Switch from
jump.
one mode to another mode.
Yeah, you will switch.
There is a mode switching effect
Okay,
here also.
thank you.
You can feel from experimentalist part of you, you just can apply some pumping mask to your sample and increase pumping power. And
Actually, also the radius of the disk is also very
Yeah, I
Of course,
slowly
of
start to grasp.
Yeah.
so we hope that in short time we will publish another paper about the burner states, what we call them, but it's not a topic of today. But thanks for the question.
We still have time to
We need to discuss all actual topics. How do we model our system? The key idea of numerical strategy to find the solution to solve that. Obviously, these equations are nonlinear, so we cannot define some kind of eigen mode here or eigen problem here. It's hard. So we should solve time-dependent problem. So we should solve time-dependent simulations. How I personally do that? There are tons of methods which allows you to solve these equations, but I used this one. It's called split-step Fourier method. It is based on Baker-Campbell-Hausdorff formula. Okay, consider if you have some Hamiltonian, it consists of two parts. First part depends on derivatives, and the second part depends on coordinates. So, actually, they do not commute, as we know. But at small time, the evolution operator can be splitted onto evolution operator which depends on coordinates, and the second one depends on derivatives. This is a numerical scheme assumption. If your step in time short enough, the Baker-Campbell-Hausdorff expansion works up to the first term, and you can split evolution operator of that system. So numerical strategy looks simplified something like that. You apply fast Fourier transform to your initial state, then you apply evolution operator which depend on momentum. Then you go back to your real space, coordinate space, then apply evolution operator in coordinate space, and then you repeat your strategy again, and after that you will evolve your wave function.
What asymptotics the commutator has in dt and delta t?
Big O of delta t in cube, delta t cubed.
And I have a question about this. And what is the goal of this? You would like to see some time-dependent solution, or you would like to know about stationary solution if it exists?
There are tons of various scenarios to which your simulations can can lead. There are stationary solutions. They usually observed near pumping threshold. There are some intermode oscillations, for example, which we call limit cycles. And so there is, I heard about some quantum chaos, some chaotic between that states. It's just, we just have to make a simulation and see what we will obtain. So we are not going very far away from pumping threshold here. So that's why we observed in this work stable stationary solutions of system and intermode interaction, usually of 2 or 3 modes. I mean oscillations in population of that of modes. So the initial condition for wave function is white noise to mimic the first stimulated scattered particle. For reservoirs, the numerical scheme is trivial. It's just Runge-Kutta first order scheme with 0 initial conditions. The boundary condition of the system is periodic because we have to use fast Fourier transform here, so it's automatically achieved. But to prevent mirror-to-mirror interactions of condensate, we have to put some strong and smooth negative imaginary potential just to kill all polaritons which can travel up to the border of numerical grid. So
I have a question about this as split step method. So when you Fourier the kinetic part and then you propagate and then you Fourier back, I mean Q space in K space, right? So usually what happens is that you, because of a round of errors, you start to accumulate some dirt, so to say, in regions where where the field actually is 0. So then round of errors may start to accumulate there. But maybe this is not an issue here because you have dissipative systems and this tiny fluctuations of the densities somewhere in kind of like empty spaces are suppressed again. Because in conservative system, this can become an issue.
Yeah. I understand. But in our system, all states with negative growth rate are tending to be killed. Just because if you expand these exponentials, you will see some exponentials with real factor and minus sign. And these exponentials will kill anything that is not coherent and growing. Of course, if your step size is in spatial or step size in time is too big, you will face disconvergences of the scheme. But we used converged one. So the practically this scheme is very convenient because if you have graphics accelerators units, GPUs, you can compute fast Fourier transforms very fast. So you just need a computer with GPU, and this scheme will be calculated fast, very fast compared to some kind of another strategies. Okay, so let me show you some simulation results. For example, this picture should be compared to one of them that I show you from experiment. So here is a pumping profile used in simulation, and after that, here is averaged wave function polariton density in real space, and of course we can apply Fourier transform to go to K space, and of course as you have time evolution, you can apply another Fourier transform to go to frequency space. So from time domain simulations, you can obtain real space density distributions, reciprocal space density distribution. You can obtain spectrum of your solution, and that's why you can plot, for example, dispersion of polaritons that were of condensate that were simulated, and compare it to experiment, for example. So by comparing dispersion and spectrum, the model is usually tuned by. So it's common practice to tune parameters of that system to match dispersion from experiment, because you can see here two modes, and in experimentally see two modes. You should tune your parameters so intermode distance in energy will be the same approximately in experiment and in simulations. So now also total two shifts.
So it's this asymmetry, left-right asymmetry in real space is due to coexistence of two modes?
These images are not final states. These images are obtained for high pump, just to say that in calculations, you can see intermode flow of polaritons. And particularly in that case, there are two modes which are observed in spectrum between which condensate starts to oscillate. And these pictures are averaged over a big span of time. So in average, you see something stationary in average time. And you should compare that to experiment. It is assumed that in experiment, experimentalists see something the same. So we can compare the simulations with some experiment. For example, here's experiment when one of mirrors was rotated at some angle. So it's hard to see something from this page because of imaging system resolution. Okay, but the pictures are similar. The next example of simulation results is a comparison of two pumping profiles, just two flat boxes and two concave mirrors, and their phases also could be extracted. And in phase, we definitely can see some focusing effect or in inter-mirrors area. Okay. There is another simulation where interesting simulation where we fixed one of the mirrors just to be a potential barrier. So one of mirrors create polaritons, one of mirror is potential barrier, and the second one mirror is just a potential barrier. It do not create polaritons. So we can see something like self-interference of polariton wave, which go to the potential barrier, reflects, and interfere with itself. Okay, it's just to view some simulation results. Okay, so experiment reminder is what we should focus our attention. We should focus our attention at condensation threshold, which was measured for cavity and anti-cavity cases. And for cavity, this pumping threshold was lower. So we should somehow understand this fact. And to do so, we can take a look just at two mirrors. One of them is concave, and the second one is flat mirror. At the bottom, you can see the particle density distribution cross-section in logarithmic scale. And for flat mirror, we see just one negative slope. And for concave mirror, we see two segments with significantly different slope. And the red one is the area when polaritons focus. So we expect from this area that in that red area, the polariton condensate interaction will be bigger than for flat mirror cases. Okay, so we can start some time domain simulations and can detect a segment at which our condensates start to grow with some growth rate. Growth rate is the slope of density versus time plot. So we can measure this the slope for each set of simulation and compare them. For just one mirror simulation, this dependence is linear near the threshold and slightly non-linear at high pumpings because at high, when density of polariton in condensate is high, they deplete exciton reservoir, and this interaction is non-linear. But this is not a topic of today's talk. We can focus at low pumping area and see that for cavity compared to anti-cavity case, the polariton condensation starts earlier. So this is the main simulation result explaining what happened in experiment. So
there is a peculiar result here that at some points the green curve has higher growth rate than cavity one.
Yeah, this is because how modes interact with each other at high pumping. But from this point, from this picture, we should know that for cavity and both for cavity and anti-cavity cases, pumping threshold is bigger or is lower than just for one mirror. We should know that we should observe that this behavior of growth rate is nonlinear, is nonlinear compared to one mirror case, and we should observe that pumping threshold for cavity is lower than for anti-cavity. All other intermode interaction is it's interesting life of these polaritons, but
I mean that you started from some statements that in cavity you will have more polaritons than in anti-cavity, but now we see that it depends on how you pump your system actually, because on this green curve has higher growth rate, and then you will have probably more polaritons for anti-cavity in some particular
particular cases, yes. But I want to insist us to go to near the pumping threshold area. So,
but it also near the pumping threshold, there's also a very small pocket where it's different.
Where they are different.
Yeah. Okay.
To somehow understand this behavior, we have to write some analyticals. I'm not very good in analyticals, but I can refer to Oleg's work where he studied interaction between two Gaussian pumped shapes. In this work, Alex reduced his system to couple or in two-mode approximation to couple of two Stewart-Landau oscillations which are written for polariton amplitudes. So all these coefficients are just overlaps, are proportional to overlaps between two condensate patterns. So we can try to write the same, and the difference between Alex and our case will be hidden in these coefficients, because the case of two mirror pumps and two Gaussian pumps differs just by overlaps between polaritons. So in other aspects, this theory should work. So as approximated eigenvalues of linearized problem which we need to solve, we used a renormalized polariton wave functions at early growth stage. When there are few polaritons, and we hope that nonlinear interactions are small, and we can treat these growing states as eigenstates of linearized problem. So we used one mirror wave function. We applied mirror transform and get the second wave function. And here are particle densities distributions for these cases. And we can use them to solve a Stewart-Landau oscillator problem. So what we observe from the simulations? First of all, at the top, you can see some cavity and anti-cavity coefficients compression at some certain pumping power, and at the bottom you can see the next. You can see compression of growth rate in Stewart-Landau equations for one mirror cavity and anti-cavity cases. The main points are the same as for simulation. We observe that one mirror Stewart-Landau growth rate is almost linear. We observe that cavity and anti-cavity growth rates are smaller than for one mirror case, and we observed that cavity pumping threshold is lower than for anti-cavity. And also their behavior of growth rate versus pump is nonlinear, as we see in simulations. Okay. Oh, that's wrong.
You should use that part to make it big again.
Photo view.
Смотреть. I fixed it. So in the same framework, we can write something like Kozhevin junction system, Hamiltonian. It's simple 2.2 Hamiltonian, in which we have only Josephson and dissipative coupling of the systems. And we can compute this determinant of the system, this eigenvalues, for anti-cavity and cavity constructed from single mirror wave function. And we observed that for huge spread of pumping powers near threshold, both Josephson and dissipative couplings were stronger for cavities than for anti-cavity. Also, to validate validate these calculations, we computed the spatial dependence of these eigenvalues to see something like Bessel function, because it also was predicted by Oleg in his two Gaussian pumps theory. So, okay. Now we need to stress the line. We used tunable concave mirror excitation scheme. We observed from experiment, from simulations, and from some semi-analytical calculations that cavity scheme supports faster condensation than for anti-cavity. Simulations quantitatively match experiment, and also semi-analytical mode captures coupling physics between that two condensate states. So the message of this work is quite simple, and we are going to publish it somewhere. Okay, that's all I wanted to show you today.
Questions?
Yeah.
Yes, please.
To a question. I think that in your calculation that you calculate this the growth rate for this the concave case, and to demonstrate yes the this
We can
speed,
go back to some.
compared with
Okay, we
the,
cannot go. We can go back.
yes the here the
Okay,
case of
let's say this.
yes,
Here.
the anti-cavity case or the one mirror case. My question is that this the concave shape. How this growth rate depends on some detailed shape of this the concave. That I think by the fine tuning this shape, you can enhance this growth rate.
There is some tuning. There is some fine tuning set of curvature of concave part. It was chosen to maximize our magnitude of polariton density in cross section. Because if you will start from just a box and go to concave, we make it more curvy, you will observe something like this. This maxima will grow, and then from some certain curvature radius, it will decrease. So we have chosen one when the particle density in cross section is maximized. So, but experimentalists do it in some. Experimentalists did it in arbitrary way. They just decided to set this curvature to be like that, like this. But maybe if we compare the effect in experiments, the effect is about a few % of quantum threshold. In simulations, we observed effect of 10%. It depends of tuning of geometry. Yeah.
I think what is also tricky is that Josephson and dissipative coupling are some oscillating functions like Bessel functions in the case of Gaussian spots, and then maybe the very fine-tuning the distance between mirrors is important just to go to node or anti-node in this periodic function. And of course, experimentalists were unable to do some fine-tuning, so in some sense they have hit the sky kind of randomly
but they observe
the distance.
And how they claim they observe this effect above measurement precision.
Yes, and possibly that is why in some very rare case we have seen that the growth rate for the anti-cavity was higher than the growth rate for the cavity. So this is why they have some different oscillations, and by this randomness, anti-cavity has locally win in this point, but still it's not typical. Still, the interaction in the case of cavity is typically stronger than in the case of anti-cavity.
Anti-cavity. The change of curvature of these plots is intermode hopping. So for certain pump power, one mode start to grow. When you increase pump power, the next mode start to grow, and so on and so on and so on. So the curvature of this of growth rate versus pump is different for different areas, segments of the plot.
Okay, no further questions. Let's thank the speaker again, sir.
And there should be some food outside. Right?
There's no letter about it.
No letter.
I don't know.
Interesting.
It's yes. Who is the first one? Please check if there's some food or not.
Yeah.
Because there was no. I don't know. No email about it, right? It's a big
No, I only
question.
have
Could
an
we
overall
pause?
communication to yesterday.
Okay.
Could we pause?
Я думаю, все посмотреть с Гауссом. Еще очень важно, что там было просто ровное число, а у вас еще есть фокальное расстояние. И вот интерплей между К и фок фокальными расстояниями тоже важен, скорее всего.
Да, то есть там получается один
Лишний
участок
параметр
фокальный,
получается, да.
другой участок уже в виде волн. Как бы, да, это, конечно, все сложно.
Ну, вы просто взяли, ну я просто взял такой как бы concavity, curvature, радиус таким, чтобы просто максимизировать амплитуду для одного зеркала.
I'm trying to stop it.
Ты это делал? Ты выбирал...
Я же тебе присылал кросс-секшены, где было показано, что для там, нужного нам этого максимального.
Максимальный вот этот участок?
Нет, для нужного нам как бы уширения всего этого добра максимальная вот эта максимальная здесь амплитуда. Ну вот в этом графике
Да.
вот эта амплитуда была, ну, как бы, чтобы была максимальной.
Это же просто амплитуда на зеркале, где в центре зеркала.
Ну и чтобы она просто была больше. Больше или ниже, она так может кататься туда-сюда. В зависимости от того, как ты блюришь или не блюришь.
В этом плане.
Да, в
Я
этом
думал-
плане.
Я
Или я не очень правильно понял.
Просто был вопрос, как бы, я так понимаю, спрашивали про форму зеркала.
Про
Не
радиус.
про
Да,
ну, за счет диффузии, а именно про радиус.
Но мы его взяли просто тогда,
Да.
как в эксперименте.
Да, слушай, я так понял, что имеет...
Я неправильно понял вопрос.